Hello and welcome again. Welcome again to graphing. I don't know what all. Okay, we're back at the front. Graphing not so simple rational function. Remember the last time we did simple rational functions, and now we can talk about not so simple rational functions. Um, Before we do, well, just to go through some of these things, let's talk about asymptotes again. When we're talking about asymptotes again, remember that in this case right here, there are lines that the graph approaches but do not touch. In most cases, well, no, in vertical asymptotes, there are lines that approach but never touch. So remember that your domain tells you exactly where your asymptote is, and vice versa. So knowing those things, you can, if you know your domain, you know your asymptote, and if you know your asymptotes, you know your domain. For example, here, if you have this function f of x equals 1 over x minus 1, you know that the domain is all values of x such that x cannot equal 1. Therefore, your asymptote, the line that your graph does not touch, is x equals 1. Cool? So we can talk about horizontal asymptotes. Remember, a horizontal asymptote, a little bit trickier, and it doesn't really abide by the rules all the time, but it's the same concept, meaning that your graph approaches this line without touching it. So that's another thing about horizontal asymptotes. Here's some quick ways we can find what those horizontal asymptotes are. First, we have this one that we went over already. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is y equals whatever the uh, ratio of the leading coefficients is. Now, the other case is if the degree of the denominator is greater than the degree of the numerator, then your horizontal asymptote is y equals 0. And then if your degree of your denominator is less than the degree of the numerator, then there's no horizontal asymptote. Let me give you some examples so you guys can see. For example, here, since the degrees are the same, then both of the leading coefficients is 1. That means the horizontal asymptote is its ratio, which is just y equals 1. Here, same thing. The degrees are the same, so the ratio of the leading coefficients, your horizontal asymptote is y equals 3. And then here, since, well, really this, remember, if it's just 1, that's the same thing as 1 x to the 0. Now the degree of the denominator is greater than the degree of the numerator. So since that's the case, your horizontal asymptote is y equals 0. Let's talk about a point. Let's talk about something that we have here. It's almost done, but I just wanted to make sure I have some markings on here just so we can get through this quick. Is say I have this function right here. First of all, let me discuss my asymptotes. Uh, my vertical asymptotes, I have no vertical asymptote. The reason why is because there is no value that I can put in here for x that's going to make my denominator 0. Notice that it's being squared and it's plus 1. So either way, whatever's here is going to be positive. So I have no vertical asymptote. However, with horizontal asymptotes, notice that the degree of my denominator is greater than the degree of my numerator. So therefore, my horizontal asymptote is y equals 0. So y equals 0 is basically just the x-axis. That's all y equals 0 is. Now, for the simple fact that I have no vertical asymptote, my domain is going to be all real numbers. So let's keep on. So basically what I did here is I used the numbers from -3 to 3. So notice here you have -3, -2, -1, 0, 1, 2, 3. So, and from there, all of those values of x, I just plugged them into this function right here and found my values of y. Once I find my values of y, I have those points and I can plot them. And you'll see that my graph is going to look a little bit like this once it's graphed. So that gives you an idea of uh, what to do when we're actually doing functions like this. So let's move forward. And once again, I have a whole bunch of markings right here just to move things quickly. And I want to show you another shortcut that we can use a little bit before. Hold on, give me a second. Uh, let's discard that, and I want to pull up my calculator. So notice that the function we're dealing with is y equals 2x squared over x squared minus 9. Instead of plugging in the values, what I'm going to do for now is, well, first though, let me turn this on. I'm going to go to my y equals, and notice that the function's already in. So since the function's in, let me come back to this in a second, is my horizontal asymptote. Notice in this case, well, my vertical asymptotes, notice I have 2 now because that's x squared minus 9. So being that my denominator is x squared minus 9, remember your denominator cannot equal 0. So that means that if that can factor to x plus 3, x minus 3, that cannot equal 0. In other words, x plus 3 cannot equal 0, x minus 3 cannot equal 0. So therefore, your domain is going to be all values of x such that x does not equal 3 or it doesn't equal negative 3. So that means your vertical asymptotes are x equals 3 and x equals negative 3. Notice my vertical asymptotes right here. Next, if I have my vertical asymptotes and I plot those, horizontal asymptotes, remember my degrees are the same. Since my degrees are the same, my horizontal asymptote is going to be the ratio of the leading coefficient, which is y equals 2. With that, I have all of my asymptotes already plotted. Next, notice how many points I use. I usually use 4 points on each side of the vertical asymptote. So I use 4 points over here, 7, 6, 5, well, negative 7, negative 6, negative 5, negative 4. I use all these points because it's on this side of the asymptote. Next, I use points in between the two asymptotes. So that's where I use negative 2, negative 1, 0, 1, 2. And then I use points on the right side of the last asymptote, 4, 5, 6, 7. And remember, I'm plugging all of those values into my function. If I'm plugging all of those values into my function, here's the part that I want to show you. Let's keep that. The part that I want to show you is that from the calculator, if this function's in, if you plug this function into your calculator and then you hit second table, all of the values are already here in the function. So you can see what the values are for each. So that means if we're starting in negative 7, go down to negative 7, 2.45. Negative 6, 2.67. So you really don't have to calculate all of those, especially if you have so many points to actually do. So we have that idea. So once you have all of your points, and once you have all of those points plotted like so, then all it is just graphing them. So now, since they're graphed like this, let's talk about the range. We already have the domain. We could talk about the range. Your range is just wherever your graph is going. All right, so notice that you have graph, you have curve, or you have purple on every single place except in between here. So let me go back. So except in between here is where you have where you don't have graph. So that means your range is everywhere except in between this place right here, right? So what that means is your range is going to be all values of y such that y is greater than 2, which is above 2, or y is less than or equal to 0. So talking about all the other places. So that, I know that's tricky, but with some practice we'll be able to get it down. The next part I'll talk to you about is slant asymptotes. We've been dealing with horizontal asymptotes, vertical asymptotes so far, but there are slant asymptotes and we have to pay attention to those as well. The way we get these slant asymptotes is if the degree of the numerator is 1 more than the degree of the denominator. Now notice when you have a slant asymptote, you don't have a horizontal asymptote. But as long as it's one more, you have a slant asymptote. The way you find the slant asymptote is just divide the denominator into the numerator. Now don't try any other way, just really concentrate on just doing long division. If you did long division, you'll be able to find out what that slant asymptote is. That is x squared plus 1. I'll put that plus 1. And out here you have x minus 1. So since this is x squared plus 1, I'm missing a term. So let me put my term in there, 0x, and I can divide. So how many, let's see, so it's x squared divided by x is just going to give you x. So x times x is going to be x squared. X times negative 1 is going to be minus x. If I'm subtracting, this is going to be x. How many times does x go into x? That's going to be a 1 right here. 1 times, to be honest with you, you don't have to worry about any of those other parts. The reason why is because you have the equation for your slant asymptote. Slant asymptotes, I should say this. Slant asymptotes are of the form y equals mx plus b. A line, basically. Notice we already have our mx plus b right there. So really your slant asymptote, in this case right here, is SA, is going to be y equals x plus 1. And to plot a slant asymptote, if it's x plus 1, your y-intercept is 1, and your slope is up 1 over 1. Those should be the 2 points that you're dealing with. So you understand that your slant asymptote, well, that's better, is just going to be y equals x plus 1. And notice how the graph approaches it but never touches it. But once you have your slant asymptote, you could just, that's perfectly okay right there. So you could just deal with just that. Well, you can do everything that you did before, do all the stuff originally. This is just finding another asymptote. So from there, you can see how things are done here. But with that information, what I want you to do is you can try to do these graphs on your own and reach out to me to see if you did them correctly or not. And you can do your 5.3 homework. So if you have any questions, please reach out to me. Take care.